Oh, continue.
All right. Okay, so let's get started. Welcome everyone to the first talk of our second season in our Trustworthy Data Science and AI seminar series. My name is Tianzi Wang. I'm a faculty member at SFU Computing Science. So together with me are Professor Jian Pei and Professor Jianan Wang, who are also my colleagues at SFU Computing Science. So today we're super excited to have Professor Carsten Binnig to talk to us about his work on democratizing data science. Professor Binnig is currently a full professor at the computer science department of TU Darmstadt. And also he's an adjunct associate professor at Brown University in their computer science department. Carsten received his PhD from the University of Heidelberg in 2008. And also spent time as a postdoc researcher in the systems group at ETH Zurich, and also in industry SAP, working on in-memory database systems, which is quite closely related to what I do. So I'm super excited as well. So currently he works on the design of data systems on modern hardware and new kinds of workloads, for example, data exploration, interactive data exploration, and machine learning as well. So he's received many awards, Best Paper Awards, Best Demo Awards, and also a Google Faculty Award. Today he's going to talk to us about towards democratizing data science. So we're looking forward to it. So without further ado, please go ahead.
So also a very warm welcome today from my end. And thanks a lot for the invitation to this very interesting talk series on trustworthy data science and AI. And I've looked into the speaker list of people who've been talking before me, many familiar, coming from the database angle where I come from. So I'm super excited to be here as well and share a bit about the research results of my group, where we visited the current data science system stack to make it more efficient and usable for end users, and thus enable the democratization of data science, as my title says. So if people ask me what the long-term vision of my research is, I often refer them to the scene in a movie, Minority Report, what is by now already 19 years old. And in that movie, Tom Cruise used an intuitive interface that allows him to answer complex analytical queries by simply using a touch-based interface and intuitive gestures. And if you look into other movies, you see very similar ideas and visions. More importantly, I think that this vision of intuitive data analytics is not just a nice vision for movies, but actually I think that it's also the way to go how data science systems should evolve, since the main bottleneck that we already see today are experts who can deal with data analytics, and thus we must work on better data science systems to allow end users with limited IT knowledge to do data analytics on their own. Now let me zoom a level deeper and contrast my long-term vision with the real world and the situation that we see today, how data-driven insights are gained with existing data science systems. If we take a look at what end user devices we already have from a hardware perspective, we already see that we are quite there. So we have very large interactive screens that would allow us to interact with data to gain insights intuitively. And those large interactive screens are just one example, and there are many more devices that provide similar ease of use to end users. So for example, in addition to visual devices, we also have devices such as Alexa or Siri that allow us to interact with IT devices using our natural language. And moreover, in the recent years, even more fancy technologies from the area of virtual reality have arisen that bring us even closer to the vision of what we've seen in the movies. However, so if you now look into the question how big data and AI systems such as Spark or TensorFlow are being used today to analyze large data sets, we see a very different picture. Instead of being usable by end users and domain users, it feels more that we are back in the age of programming on punch cards, since for using the big data machinery, actually a data science expert is needed for programming the machinery, and getting insights out of the data can take days or even weeks. And now to better understand where the current pain points are, let's even zoom one level deeper. So if we look at a typical scenario of how insights are gained from data, we often see the following picture. First, a domain expert such as a medical doctor, for example, needs to involve the data scientist who translates the hypothesis of the domain expert into a data analytics program that can be run on the collected data. Already this first step can be typically tedious, since often many iterations are needed until the data scientist really grasps what the domain expert actually wants to see, and then needs to refine his program once he gets a better understanding of the domain that where he's analyzing the data in. A second pain point that shows up when the data scientist then actually runs his data analytics program on a large data set. The problem here is that a single run can take hours or even days until the data is analyzed. And even worse, once the data scientist comes back with a result, the domain expert typically has new questions that starts the very same inefficient process over and over. And finally, what people often forget when talking about data science is the fact that many of the steps are really labor intensive and require huge amounts of manual efforts. So one important step which causes extremely high manual efforts, for example, is data cleaning. That often can eat up to 80% of the time in the overall efforts in many data-driven projects. So hence, in my research agenda, I'm following the problem to revisit the data science systems and address them from a more practical systems-oriented approach to make them more usable and address these individual pain points. More precisely, my research agenda that I'm currently pushing forward in my group is grouped into 3 lines. So the first line of research is to rethink systems from the angle to enhance human efficiency. So here we work a lot on new interfaces for data analytics that can directly be used by domain experts, and I will later on show some examples of those interfaces. A second line of research then also addresses the aspect of systems efficiency to increase the overall performance of scalable systems by making use of modern hardware technology. And this is what Jan Zeng was referring to. I've been working on main memory-based systems, and we've done a lot of work in how to, let's say, build distributed, scalable main memory-based systems in the past. And as a last line of research, which is the newest line, I would say, that I added to my group, I'm looking into the automation of data science, which kind of glues the human efficiency with the system efficiency. Because nice interfaces are good, but if the user still has to do a lot of steps, it's inefficient. And even a fast system doesn't help here. So what we really want as the glue between human efficiency and system efficiency is automation. So take away the labor-intensive work of the humans as much as possible and let the systems do it. But only those steps where, let's say, the human is not really helpful. So automation must be done carefully. So, and as I said before, in my research, I take a very practical systems-oriented approach. And in fact, we aim to build a new data stack for data science systems in my group and bring together the research of these different lines that I just mentioned. So what you see here is a sketch of how the stack could look like based on the individual systems that we are currently building in my group and we've built in the past. And the end goal is really glue these systems together. And in research that takes a bit longer, but this is actually, if I would look at the long-term vision, this is where I want to be in a few years then. So in order to address the human efficiency, we revisited, for example, user interfaces for data science, which includes visual and natural language interfaces for data analytics called dbPAL and Wisdom, so the top layer of the stack. To avoid manual work, we've also recently started a system called MLPAL, which is a system where we want to plug in various components to automate the individual steps of data science pipelines, such as data cleaning, but also other steps, such as making model building more automatic or other steps in the data science pipeline, and come to that later in the talk as well. And finally, for the backends to process the data in a scalable manner, we take a twofold approach. On the one hand, since many systems are already in use, such as Spark or TensorFlow, we aim to integrate those systems in the layers above. So we don't want to completely replace them because we think they are already there and should be used. But on the other hand, we also build our own backend systems to make the scalable processing of data more efficient. For example, a system that we are building in my group is called NumDB, which uses modern hardware technology and network technology, especially such as remote direct memory access, to speed up distributed computing for various workloads, ranging from classical database workloads to more involved workloads, such as machine learning. In the following, I will now walk you through some of these systems, not the complete stack, but some of the systems that we've built in the last years, And I'm happy to talk about any of the other systems that I'm not covering today in the question and answer round after my talk. So let's start with dbPAL, which is a system that provides users a natural language interface for data exploration to increase the human efficiency in data science. So the first question you might ask is if natural language interfaces are actually needed if we have already visual interfaces such as Tableau or our own wisdom system that you see here on the left-hand side. And my answer to this question is, while visual interfaces clearly allow end users to use or do data analytics in an intuitive way, natural language interfaces are an interesting alternative since they often provide a very concise way to query data. For example, if you look in this at the slide, you see a situation where a user asks the questions of how many females older than 30 survived the sinking of the Titanic. And what you see is that the visual interface requires multiple steps of interaction, so dragging out multiple visualizations that visualize the data on the different dimensions, so the geolocations, the age groups, the gender, and then you need to link them together to come to the final conclusion of how many of the 30-year-old female passengers died, to see that actually none of them died and all of them survived because they were the first ones who got into the rescue boats. But what you see here is that with a visual interface, it takes many interactions, but with a natural language interface, you can simply post the question that is here on the slide in the natural language form. So just type it in, and the user would be then just able to shoot out that question to the data analytics system. And moreover, another advantage of a natural language interface is clearly that the interface can be used in a hands-free manner, and thus is usable in situations where visual interfaces cannot be used, for example, by medical doctors, if they are, for example, busy doing other things or while driving. However, a challenge when building a natural language interface for databases is that users pose questions in various forms, and thus translating those questions into an executable data analytics program is a hard problem. So here we see an example of different categories of challenges a natural language interface has to deal with, for example, for a medical database where the end user might use different ways of paraphrasing the very same question or leaving out important information in their questions that are implicitly clear to humans. For example, when a user asks for fever patients, it is clear that fever is a diagnosis and not a name or something else. However, for a system that provides a general natural language interface for data, the system must be able to infer this information from the user query. So being able to support these various forms of how users can ask the very same question is a huge challenge. And even in addition to these paraphrased and incomplete queries, there might be ambiguous queries where the system requires feedback from the user, which is a thing we are not yet tackling, but we want to tackle in future. For example, if you ask a question like how many patients with fever come from New York, New York might be actually the city or the state. And if you have both in your database, you might want to ask the user back which one the user actually wants to refer to. In the talk, I will focus more on the upper parts, so how we can build a robust natural language interface for databases that can deal with paraphrased queries and incomplete queries. So when we started this line of work, which is actually now a few years back, deep learning was just at the rise, and we thought, oh, this would be a good idea to the rescue to build a robust natural language interface also for data analytics, since deep learning showed remarkable results for similar tasks to what natural language interfaces do today for databases. Actually, what a natural language interface needs to do is to translate a natural language query into some form of executable program, which could be, for example, SQL if the data sits in a relational database. So our approach was to tackle the problem as a language translation task and use state-of-the-art deep models for the task to build a robust natural language interface for data analytics. So if you now look into how deep learning models are being trained, it quickly becomes clear that the problem is the training data required to train those models, right? So in general, deep learning in general training for deep models, you train the model for a specific task. So if you go back to the example of machine translation and you want to translate English to French, you need a lot of sentences where you have the English and the French translation that you feed into the learning process. And so to train a model for example, for language translation, you can use various forms of collecting training data, for example, crowdsourcing. And you could ask crowd workers to translate given English sentences into French, or you could use some existing texts where already the translation is available, which is often done in machine translation. However, if you map this problem to natural language interface for database, you can see that for a given database where you want to build a natural language interface for, you need pairs of natural language to SQL statements that you can use for training that specify how natural language questions should be translated into SQL. However, that is already problematic on its own, since the number of people who can provide SQL statements for natural language questions as translations are clearly limited, and hence crowdsourcing is likely not a good idea, right? And moreover, there are also not many corpora around that contain pairs of natural language and SQL statements that you could use for training such a model. And moreover, even worse, if you have such a training data set for one database, if the next database comes or the database schema changes, so you add new tables or change attributes of the tables, the training data collection needs to be repeated over and over. And so this is also the problem where we started to work on. So our contribution is not a contribution where we develop a new machine translation model, but it's more the question, how do we build a robust training natural language interface by providing better training data and avoiding this high effort for training data generation. So what we did for dbParl is that we decided that we go a different route. So instead of relying on manually curated training data, we decided to synthesize the training data from a given database schema. This notion in machine learning is called weak supervision, where a weak signal, in our case, the database schema, is used to synthesize the training data. And the main idea on how we generate the training data from a database schema is that we use a two-step approach. So first, we take a set of SQL templates to generate a variety of possible SQL queries for a given database schema, as well as a naive natural language translation for each SQL query that is specified in the template. And I will show you an example in a minute. And afterwards, in a second step, so the second box, what you see here on the slide, we then use an automatic augmentation step, which is crucial since this varies the natural language part of the first step for each pair to cover a broader spectrum of how a user might ask the very same question. So now let me show you an example to make this a bit more intuitive. On the left-hand side, you see actually a simple database with only one table for the purpose of the example, and a template that we use to generate a natural language and SQL pair. This template, for example, specifies a simple SQL query with placeholders that we then will fill in from the given database schema. And clearly, we have many of those templates. And here's just a very simple select from where query with a corresponding translation. But we also have aggregate queries, aggregate group by queries, also templates for more complex queries. As a result, from expanding this template, we then get several natural language SQL pairs, even from this one template already, because we fill in the slots with the different attributes, for example, and we generate different filter criteria. And it is important to note, as I said, that we have several templates, and the same template can be expanded multiple times. So here we already get a huge variety of natural language SQL pairs in this very first step where we expand the templates. And after the template expansion step, we then apply the augmentation step. And the idea of the augmentation step is similar to data augmentation for image data, for example, where the same image in a training data set is cropped, for example, or rotated to make the model more robust. However, for dbParl, we don't have images, we have natural language SQL pairs. And what we do here is we augment the natural language part of the natural language SQL pairs, meaning that we vary the natural language part multiple times. And more precisely, what this means is that we use various forms of augmentation, such as automated paraphrasing, which you see here above. So we take the simple natural language statement that is it comes out of the template, and then apply paraphrasing to transform this into a different query. And for the paraphrasing, we use existing paraphrasation models that have been trained on larger corpora available on the internet. So they bring in a huge variety that is not actually encoded in the database or in any of our templates. And we have many more techniques for data augmentation, such as noising, where we remove individual words from the natural language query, as well as other techniques that I'm not covering in the slide. And as a result, even for a simple database with just a simple table like this one here, we can generate millions of different natural language SQL pairs that we can then use to train our natural language to SQL interface. So now, for showing how well our approach works, we have evaluated in several real-world data sets and compared dbPaL to different baselines. So for example, we use a classical non-learned natural language interface here called Nalia, which was also published in the database community. And this represents more a traditional baseline that uses more a rule-based interface for query translation. Moreover, we also compare to other learned approaches clearly that rely on deep models. And here we used a baseline at that time that was called Neural Semantic Parser, so NSP. And NSP comes in two flavors: a base variant, which does not need training data similar to dbPaL, and also uses templates to bootstrap data generation. However, they don't use the augmentation step and only use a very limited form of templates. But in addition, they allow, for example, that the training can make use of manually created training data, and they call this model then NSP++. Then, as we've seen from our experiments, dbPaL is superior to all of these baselines on the patients database, which is a medical database. Here, NSP++ could not be trained since no manual created training data was available. So we used just the template approach that they provided, and you see here that so with the template approach, which is NSP, without the ++, the accuracy is pretty low. For the geo database, however, which covers geological information, manual training data was available and was used for NSP++, and in this mode, it outperforms dbPaL. However, we looked a bit closer into the training data that was used for NSP++ and found that the training data and testing data actually cover a lot of identical natural language SQL pairs, which eventually explain the high accuracy. So we are not really sure if you would use it in a bit more broader, generalized setting, if it would provide the very same accuracy. But again, also from our end, there's a room, as you see, for improvement. So with our synthetic data, we achieve on this more complex database schema of GeoQuery a lower accuracy, but compared to, let's say, the NSP++, which uses only templates, so NSP without ++, which uses only templates, we see a huge improvement. So NSP, the template only achieves accuracy of 5% on this benchmark, whereas we achieve 55% correct translation. So to wrap this part up, here's a short demo of what you see, where you see dbPaL in action. And I let the video play for a few seconds and then move forward in the interest of time. But I can share my slides eventually with Tianzheng. And if people are interested in watching the full video, the video would be contained in the slides. So here you see at the beginning, very simple queries that the user is asking, going to more complex queries. Now, average query, what is the average length of stay? And then you see that it's translated into in what SQL query it's translated into. Now it's users adding a filter criteria for female patients only. And later on, we also would see cases where incomplete information is used, such as patients with flu, where the diagnosis is left out in the query. Good. So let me now come to the second part of my talk, which is about a more recent system we started to build called MLPaL, which is the system to automate labor-intensive steps of data science pipelines, as I mentioned before already. So if we look into how data science pipelines are composed today, we see a very similar picture as the one I showed at the beginning, where a domain expert must interact with a data scientist who then is implementing the individual steps of the data science pipeline to derive insights from data. And at the beginning of such a pipeline, typically relevant data sources need to be identified that might be helpful for the task at hand. And afterwards, the selected data must be cleaned and then can be used for further downstream tasks, such as learning a predictive model or making a decision based on the data using more traditional tools, such as data warehousing or OLAP. However, as mentioned at the beginning of this talk, already many of the tasks to create a data science pipeline are labor intensive and cause not only high manual overhead, but also require deep expert knowledge for each step. So what we aim for with MLPAL is an automation of the individual steps to help end users not only to speed up the creation of ML pipelines, but eventually also allow domain experts without expert knowledge in the area of machine learning to directly compose those data pipelines themselves. However, we do not aim for an end-to-end automation of the full pipeline. It's not our goal to completely remove the data scientists, but really allow the end users or support the end users in composing the individual steps, or even supporting the data scientist himself instead of the end user in composing those data science pipelines. Thus, in MLPAL, it's designed as a system where we can host many individual tools that automate the most important steps along the data science pipeline. So, for example, we have systems to automate, let's say, the data cleaning part, which I'm showing in a minute, but also systems that help with automatic model training, so to replace the labor-intensive parts there. In the following, as I will present one such concrete system called Restore, which is for automating certain data cleaning steps, especially when it comes to solving problems with incomplete data. And luckily, this paper was just recently accepted to SIGMOD 2021. So we are happy to present that soon in the next version of SIGMOD. So the main motivation of Restore is that the main tool for decision making in many enterprises today are still data warehouses to answer OLAP-style aggregate queries, such as what is the total revenue of the last years. So it's not so much into machine learning, but it still requires that data is cleaned and stored in a data warehouse before it can be used for analytics. And the fact that OLAP-style workloads are an important class of analytical workloads is supported by the fact that many of the cloud vendors have started to build their own cloud databases to enable scalable execution of OLAP queries on large data sets. And as I mentioned, the traditional assumption of those systems is that the data sets that are loaded into a warehouse come from internal, well-curated enterprise data sources, and thus the data was considered complete. However, in the recent years, enterprises want to use also data from external data sources for data warehousing. And these data might come from external open data sets. And usually what people then do is put them in a data lake first, don't clean them, and later on, when you need them, start the cleaning. However, a huge problem when you use these data sources and when it comes to cleaning is that these data sources are incomplete, and it requires really a huge effort to deal with that incompleteness in the data. So what am I meaning with incompleteness? I'm not talking that, let's say, in individual rows, individual values are missing, but really that complete rows of a table are missing. And to, let's say, show this and give you an intuition what this means, let me give you an example of what I mean with an incomplete database. So if you look at the incomplete database here, which would be for a housing database from the US, we see a database with two tables, a complete neighborhoods table that lists all neighborhoods for all states. And this might be a curated list that you have in your database anyways. And then you got an incomplete list of apartment tables coming from an external data source. And incomplete here means, as I said, that tuples in the apartment tables are missing, since, for example, data is not available in all neighborhoods in all states, but only in some neighborhoods in some states. And having such a database with complete and incomplete tables can have many reasons. One of the main reasons is that often data is not available for certain subsets of your database. In our example, it is because, for example, the data did not get published by a certain state because, for example, of legal issues. But there are many other reasons why data could be incomplete. For example, there are situations where data is systematically missing because, for example, if you think about certain cases, you might not be able to even collect data for certain subsets of your database. Moreover, in addition to systematically missing data, there are many other reasons why data can be incomplete. For example, if data is coming from an external source, as I mentioned before, you don't have any control over the data set, so it might be also incomplete because of that reason, or simply because data collection is way too expensive to collect the full data set. So for example, typically in survey data, you only get data from a certain subset of the population instead of getting a full data set. The problem, however, with incomplete data for decision-making with OLAP is that those queries, if you execute them directly on the incomplete database, the result will be highly inaccurate and thus lead to erroneous decisions. However, fixing incomplete data is not a trivial since this is a challenging task for different reasons. So first, incomplete data might be highly biased. For instance, in the incomplete housing database, there might be more apartments from states with a dense population, and thus these apartments have higher rents because typically the data that is available in those densely populated areas, the apartments have a higher rental price. Second, fixing incomplete data is not trivial since many correlations might exist in the data that span across several tables that have to be respected when you create the missing data. So for example, one correlation that I already mentioned is that high density means a higher apartment price. This is different from bias because bias means that you might have less data for lower price regions and more data for higher price regions. But the correlation itself is also interesting because that informs you how you need to generate the data. So hence, in practice, missing data is often simply ignored, and it's just assumed that the available data sample is somehow representative. Hence, often the problem is, as I said, ignored, and the sample is just used to make decisions on. Another way to deal with incomplete data is clearly to manually create the missing data. However, as I mentioned above already, this is an expensive and complicated process on its own. So what we do with Restore is that we've built a system that can automatically synthesize the missing data. And the main idea is that Restore uses the available data as evidence to synthesize the missing data. For the completion, Restore exploits various signals in the available data, such as correlations between attributes, but also correlations between tables, but also how the data is distributed across tables. So how many apartments a typical neighborhood has based on the attributes of the neighborhood, such as the population density in the example. So in Restore, we make use of those signals and learn so-called neural completion models that are based on deep autoregressive models to capture all these signals. And at runtime, we then generate the missing data for a given aggregate join query at hand. So for example, to answer a query that asks for the average rental price per state, Restore would generate the missing data for the states without apartments to answer such a query. Now let me also zoom a level deeper here to understand how, let's say, the training phase and the query phase, so the offline phase for training and the online phase for querying actually works. So to learn completion models, a user has to first annotate a database schema. And this is a lightweight task because the user only has to say which tables are complete and which are incomplete. So here in the example, we have a schema with two tables, landlords and neighborhoods, which are complete, and incomplete apartments table. So similar schema as you've seen already before. And we additionally need to carry out an automatic pre-processing step where we derive so-called tuple factors for the relationship between the available data in the complete and incomplete tables. So for example, in our case, all data of the apartments in New York are available in the incomplete apartment table, and thus we would derive tuple factors for this neighborhood. So What this means in the example is that the tuple factors describe how many apartments a typical neighborhood has based on the attributes such as population density in the neighborhoods. And this tuple factors can be used then later on for informing the completion models on how many missing tuples for the other neighborhoods should be generated. So after the schema is annotated and the tuple factors are computed, we train our neural completion models, and I'm happy to talk a bit more later in the Q&A what models we are using. I'm not going to depth here, but we train the models on the available data, so on the available complete data from the complete tables, as well as the available data from the incomplete tables. And what is important that both these steps, the annotation and the learning process, are query independent, meaning that we can reuse these models for various queries that we later on ask over the different tables if we, for example, join apartments with neighborhoods or apartments with landlords. So once the models are trained at runtime in the lower part, you see that we then use the completion models to answer accurate queries over incomplete and complete tables. So I already showed the example query. So here this query asks for the average rental price in the different state, and therefore joins the complete neighborhood table with the incomplete apartment table. And here, as I said before, we would generate the data for the missing neighborhood, for the neighborhood with the missing apartments, which would be here the neighborhood in California, sorry. Good. To show how well Restore can synthesize the missing data, we have conducted experiments with two real-world data sets. A housing data set that is based on real-world Airbnb data, and a movies data set, which is based on IMDb. And for making these data sets incomplete, we've removed tuples in a biased manner in various forms to synthesize an incomplete database for our experiments. And the nice thing was that we then had the ground truth, so the complete database available to compare the accuracy of our restoration. And so for each of these data sets, we have defined 5 different setups where we've removed data from different tables based on certain attribute values. And moreover, we have also varied different factors. So for example, how much data we keep in a table, called keep rate, and I show that later on in the experiments, as well as how much bias we introduce by removing, which is a factor called removal correlation, which introduces the bias in the incomplete data. For example, that apartments with lower prices are less likely to be in the database, and apartments with higher prices are more likely to be in the incomplete database. So as a result, what you see here in the experiments is that we report a metric called bias reduction for each of these setups. And H1 to H5 denotes the setup for the housing database, and M1 to M5, which are the different plots here, represents the different setups for the movie database. So each setup is, we remove different data from different tables. And on the x-axis, you see that we varied the removal correlation, and the different colors stand for the different keep rates, meaning how much data we kept in our incomplete database, ranging from really few tuples only, or few entries in a table only, to a higher number of entries. And what you see is that Restore can, in many setups, remove bias, even sometimes completely. And the varying accuracy stem from the fact that the predictability for the synthesis data clearly varies, since data of different tables is removed for the different setups. So if there is, let's say, if you remove data from a table which is independent of the other tables, the model has really is not that good in predicting what is missing, right? So the signals must be strong, so to say. In the paper, we therefore also provide a way to compute confidence bounds on the generated data, which I'm not showing here in the talk, but the intuition is that it tells us how certain the model is when generating the missing data, meaning that if it's uncertain, also the bias reduction would be maybe not that good. But there could be also cases where we, let's say, remove bias, let's say, or we can reduce the bias reduction much better but the model would be still kind of insure, and then the confidence bounds would tell us actually that the model was insure when generating the missing data. And another important factor is that what you see is that Restore can deal with different forms of keep rates, so with low and high keep rates, and also with high and low removal rates, which shows that Restore is actually applicable in a wide range of situations. So yeah, maybe let me now conclude. So I'm coming more towards the end of the talk. So today I've presented you the overall research vision of my group, where we want to revisit the complete data science system stack. And I exemplified some of my work by showing you two systems, so MLPAL and DBPAL. And I haven't shown you other systems like Wisdom or other results that go more in the lower parts of the stack, where we focus on modern hardware to speed up data analytics, for example. But as I said, please feel free to ask questions if you are interested in that line of work. I'm happy to answer them after the talk. So to wrap up, let me list some of the steps how I'd like to move forward in the next years. And clearly the work on MLPAL just has started, and there are many more directions to work on the automation of ML. But we also have other areas that we currently working on. For example, we are also using machine learning to optimize systems. So here it's going again more in the systems efficiency angle. For example, we are using learned approaches to optimize the data partitioning in distributed data processing, or we work on learned optimizers to make query execution also more efficient in a distributed setup. And finally, let me mention that I recently funded a startup on something called Trustworthy data sharing, called Trustable, which would have maybe also have been interesting for the series if I think a bit about a minute, because this seminar series is called Trustworthy Data Science and AI. But yeah, since we are at the beginning there, I think this talk was eventually a bit more with more beef and more meat. And yeah, maybe let me talk about Trustable in a few years in future then. Good, with that, I'm happy to wrap up and thank also many of my collaborators that I've been working in the past years at the different places where I've been. So many collaborators at Brown that I've been working with, but also in my recent position in Darmstadt. I'm happy to work with my machine learning colleague, which is shown here on the top left corner, whose name is Christian Kersting. And I especially enjoy working with him because we have actually really extensive and deep discussions about how we better integrate databases and machine learning. And clearly all this wouldn't have been possible with a sample of the students that I'm showing here. So I couldn't put all of my students yet here. It's not up to date. But many of the students that are behind the work that I've shown today are on the slide, and also a big thanks to them because, as I said, without them, all this breadth wouldn't be possible. So yeah, let's conclude. Thank you for your attention, and I'm really happy to take your questions now.
Thank you very much for the great talk. Yeah, I do hope to hear more about Trustable in the future. So yes, so now let's, if you have questions, please feel free to just unmute yourself and speak up. Maybe also turn on your video camera, or you can also type into the chat window. So I will just read out and then for Carsten to answer.
Yeah, I'm seeing one on the chat, but I could also take other questions first.
Right. So I guess, yeah, so from the chat, the question is like, how important are those templates used to produce training data? This is for the NL2 SQL project, particularly the natural language description templates of the questions.
So the templates are important in the dimension of what SQL queries are supported, because they really define what types of SQL query DBPAL can translate natural language queries to, right? So if a certain query class like nested queries wouldn't be covered in our query templates, there's no way in translating into such a query. So here we think we already cover a big breadth of different SQL queries, but clearly since SQL is composable, you can never be complete in a sense that you can cover all the different SQL queries in your templates. From a natural language perspective, though, as I said, we use this augmentation step. So the templates are really just there to bootstrap an initial version of a natural language translation for each SQL query, right? So, and the augmentation step then creates many different variations for the very same natural language statement. And here, the idea is that we really, by this step, we get the robustness of dbPAL towards different ways how users can ask questions against the database. So yeah, templates are kind of limiting, but as I said, on the natural language side, we want to be robust, and hence the augmentation here really helps.
Hi, this is the man from engineering science. I'm a faculty member in computer engineering, and I work on hardware acceleration. Very nice talk, thanks. In your big picture, you also show that you work on the hardware accelerations using like GPUs and FPGAs to accelerate this database. I'm curious to know what kind of challenges and opportunities that you see for this GPU and FPGA acceleration for the database.
Yeah, so maybe let me comment in two parts. So where I come from is, so originally I've been doing a lot of research in scalable distributed databases, and so we've done a lot of work there, just also on traditional, let's say, data partitioning techniques, but also distributed transactions. And the modern hardware part, what we first started, is a line of work where we looked into how modern network technology can speed up distributed query processing. And so we've done in the last years a lot of work on RDMA and extended this line of work also in the direction of in-network processing. So how we can offload some of the processing to the network, since network cards and switches are getting more programmable. And in that context, so I've done a bit of work also with accelerators that I'm adding at the moment bit to my research portfolio. So for example, for the in-networking part, the currently available hardware is limited. So you have the P4 switches, for example, but if you know P4 as a programming model, it's very limited. And here we, with a colleague more on the computer engineering side, Andreas Koch, who's doing a lot of work on hardware architectures. So we've designed a new switch architecture which places FPGA into the switch such that we can get around the limitations of what P4 as a programming model, but also the processing pipelines in the switch have. Moreover, current switches have only limited, let's say, memory to store intermediate state. So we also looked a bit into how we can use modern FPGA boards with high bandwidth memory and higher, let's say, memory capacities for the switch, or to build the switch to provide more, let's say, a platform that can support more complex database operations while data is transmitted over the network. So my experience with FPGAs is based on that project. And for GPUs, we are using GPUs also in a distributed setup, but not for in network computing. But here we look also into the intersection of fast networks and GPUs, because with fast networks, you can, for example, directly copy data via GPU direct into GPUs, and use GPUs here also for distributed processing. And the main motivation here is that we think since in many distributed applications, data anyway needs to be transferred over the network. And here, if you look into what RDMA provides, is that it provides the same speed for transferring data to a GPU and a CPU. Because if you transfer over the network, you are limited by the network. And then if the end, let's say, device where you copy data to is a CPU or GPU, it doesn't matter. And hence, finally, in this setup, GPUs pay off for distributed data processing. In a local setup, they usually don't, because in a local database where you have local memory attached, the GPU is just much slower. And therefore, we go in the direction of using GPUs in a distributed setup. So it's also not that that we have extensive, let's say, work on using GPUs for data management, but also, again, in this intersection of networking plus GPUs as an accelerator in the network, so to say. So that's a bit, let's say, that what we've done. And now my perspective. So I think what is really challenging with accelerators, but this is something that I think everybody is facing. So we add a lot of complexity into the system. And what makes it hard is now really building a sustainable stack where you, let's say, on the fly decide what is the best accelerator to use for your workload. And we are far away from being there. But I think a huge challenge is really heterogeneous computing is coming up because of several reasons, but really how do we program them in a manageable manner that in future we don't have a zoo of different algorithms and that we get something, a system that can automatically compile down or use these accelerators in a more seamless manner is something that I think is important for making them really usable, but yeah. We are far away yet from that, and we are really more looking into how we can use them for the different data management tasks.
Yeah, thanks. Yeah, that's very helpful.
A long answer, sorry.
Yeah, I mean, yeah, my group works in the in this area. I'm not well, we're kind of new to the database, the application domain, but we actually. We're more specialized in the heterogeneous systems. We try the different some other application domains actually had some successful stories like genomics and machine learning. Yeah, maybe.
Yeah, the problem here is that if you, as I said, so accelerators, so there's a lot of work on accelerators in databases, but very often the problem is that what you want to do in a database with SQL, so it's not that computational intensive, right? And very often the overall time that you need is when you include an accelerator is dominated more by data movement to the accelerator and back. And if you are not doing this carefully, then the accelerator might be actually a de-accelerator because it slows down the query processing. And so we are looking really into let's say situations where data anyway needs to be shipped, and maybe when data is anyway transferred, is there a point where you can plug in a accelerator that helps you transforming the data if it's anyway if it anyway needs to be moved. And this is this thing we did for GPUs. So if data needs to be moved, for example, for a join, then instead of shuffling the data to CPU cores in a distributed setup, you can shuffle it to GPU cores. But since shuffling is similar expensive for both endpoints, it actually then pays off. But yeah, therefore, you have to be careful when to apply accelerator for databases, I guess, as one of my takeaways, which is more practical, but I think it's often ignored in research.
Yeah, thanks. Yeah, I may follow up with you offline. So yeah, I'm
happy.
Area. Thank you.
Hi, this is Jianpei. So I have one technical detail question and one big question. The technical detail question is that for the NLP translation, you mentioned the templates, you use data augmentation. So have you ever try or consider to say, for example, use an English template to describe the query and translate the English sentence to German, for example, and then translate it back to English so that you can add noise to the language. And as a byproduct, you may also harvest multi-language, multilingual, NLP interface.
Yeah, so very, very good point. And actually, so cross-language translation, so translating from, let's say, if our target language is English, so if we we actually do this cross-language translation, translate to French and back to get paraphrased queries as well. So this is one of our techniques we apply. So we are not yet multilingual, but this would allow us to be also multilingual. And instead of having only English natural language interface, we could directly get a French or German natural language interface from the very same technique. But we haven't gone in this direction yet.
Okay, so the bigger question is that you mentioned the trustworthy data sharing. So in that big project, what's your vision or definition of trustworthy there?
Yeah. So the problem that we are trying to solve is twofold. So trustworthiness can, in our eyes, be defined in two directions. So one is, so for the person publishing the data, very often there are legal constraints or other policies that you have to obey when you want to share data, right? And very often data sharing doesn't work because the data owners are unsure if they really fulfill all these policies. And here, trustworthiness from a data owner perspective would be, so we want to build a system that automatically ensures the data owners, if they publish their data, that they are in line with the existing policies. On the other hand, data owners also need some form of trustworthiness, right? They want to make sure that if they consume the data, that this data has a certain quality. And if, let's say, somebody, if you share medical data, as an example, if there are wrong values in there, you want to know who actually did publish the data and eventually who did the data change on a shared data item. If you think of a shared database with patient records and you share data and a hospital takes that for making a decision, for example, how to treat a patient, then you want to be able to trace back who did the data change, also for example, for legal reliability. So here the question is also trustworthiness is on, let's say, being able to audit and trace data changes back and see actually who did changes to what data item, etc. So it's in both directions, trustworthiness for data owners, but also trustworthiness for data consumers.
Great. Yeah, by the way, thank you so much for this wonderful talk. It is really exciting and inspiring.
Thanks.
Do we have more questions from the audience?
I'm trying to see. The chat isn't, I don't see anything in the chat at least. So, yeah.
Maybe I can ask one question. It's a very interesting talk. Thanks, Carsten. So you talk, the title, you call it towards democratizing data science, which means that we are still far away from that. So what do you think is the biggest challenge, because you laid some future direction, what do you think the biggest challenge that stop us from reaching there? So imagine we are able to reach there. Does it mean that we don't need data scientists anymore in the future?
Maybe let me also first start with a down-to-earth answer. So I think, so with democratization, I think the end goal will not be to, let's say, remove the data scientists completely, because there are always tasks a data scientist should do. But the question is, what tasks should the data scientist do and when should he be involved? And this is when he's most efficient, right? And in very many situations, so initial data exploration, for example, you don't need a data science scientist to be involved at all. In my bigger vision, there's still a data scientist, but the question is, so when does he need to be involved? And the second question is, so what tasks can, let's say, we automate because of that, right? So some of the tasks data scientists are doing today are clearly the plumbing tasks of putting together data science pipelines. And these are the targets that I want to automate with MLPAL. What is the longer term vision and what are the bigger challenges? I think the biggest challenge is that this is a team effort, right? There are so many disciplines involved, and I'm a database person. and I can only solve parts of it. And I think so here we really need to get into team sports, bringing together the different people, going really into the core of machine learning, but also my colleagues here in cognitive science are really, let's say, I think they need to get involved at a point, because they think or ask questions like, what is the best way of involving humans and best presenting information to humans? And this is something where I'm not really, let's say, an expert in. And so bridging this gap between different experts on the CS side is actually, I think, the biggest challenge for that. And I'm happy here to be here in Darmstadt, because I have colleagues that are really willing to spend the time together to discuss this, not just on the superficial level, but really spend this in a more depth discussions. So therefore, I think team sports of the different disciplines is really the bigger challenge, and from that we will see also what is needed to really make this vision happen at the end.
Thank you.
Okay. Do we have any more questions? Or I actually had a quick, I guess, clarification, or just wondering, for the like getting the training data sets, like synthesizing the training data sets from the schema, like what would happen if, like say, I add a column or remove a column, those kind of schema changes, or changing constraints and so on? How would this approach evolve in that case?
Yeah, so at the moment, we don't track any incremental changes, but you could simply rerun our data generation pipeline, right? So you would generate a new set of training data, because templates are just instantiated by the different schema elements. And if there's one more attribute, you could definitely, the training data would include this, right? And a more clever way would be to just generate the new data for the schema changes and then do incremental training of your machine learning models. But this is, this is clearly a thing you could do, but we haven't done so.
Okay. Yeah, so I was reading other papers, like in some cases they change the schema quite often, say once, maybe on average a month or a week. So do you actually see like these happening in the kind of workloads that's being considered here? Or like, is it actually common, or it's not really a big thing here?
Yeah, from my, let's say, time at the industry, I was working in a data warehousing group, and I think also the schemata people are having there are quite often changing, not maybe on a daily basis, but still they want to integrate new data sources, meaning they add new dimension tables, or they extend existing dimension tables in a data warehouse. So I think in a practical setup that happens quite often in an enterprise. And therefore, being able to extend your analytics interface automatically to cover those schema changes would be interesting. Yeah.
Mm-hmm. Yeah, thank you. Okay. Don't see any questions from the audience at this point. Maybe everyone is hungry for lunch here.
Yeah, for me it's dinner time, so I'm. But I'm happy to take more. So just there, the chat, there was just a quick comment, no question.
So if there are no further questions, probably we can wrap up. Yeah.
Okay. Yeah. All right. So last round of asking for questions.
If not, I'm happy to take also questions offline. If so, I think Jian Zheng, or you have my email address, or it's also public on the webpage.
Right.
So anybody who wants to follow up on something, just send me an email. I'm happy to answer also these things then offline.
Right. Okay. So thanks everyone for attending our today's talk. And well, one last thing as usual. For upcoming talks, please visit our website. I think so you can Google search actually like Trustworthy Data Science AI Seminar SFU. Should be able to reach our website for upcoming talks. We have a fantastic lineup of speakers, including Carsten today, to come in the next 3 or 4 weeks. Okay, so thank you everyone again, and see you next time. Thanks, Carsten, for
thanks for the invitation and for the many interesting questions.
All right.
Thank you very much, Carsten.
Thank you.
Yeah.
Thank you.
Have a nice
Good
evening.
Carsten.
Yeah, you too. Bye-bye.
Bye.
Bye.